That would be pretty
I thought
cool.
that was a good idea. I don't know if Mountaineer is still offering.
Okay, so we can talk about those later. Let's have a class. We have left a little bit of the fatty acids. So we want to talk about polymorphism of fatty acids. So this started with this polymorphism, which is polymorphology. You can understand that. So we started talk about is solid become liquid. So let's say we have a fat, and it's not really a solid. We usually call it a semi-solid. So give you a very simple example is we had a chicken soup. So chicken soup with chicken piece there with the soup. Then we put in a refrigerator, so it's like glued together, very sticky. And it's semi-solid. We also call it a plastic status. Then you said you want to have a lunch, so you put the whole bowl into the microwave. So you heat it, and you heat it, then it becomes a liquid. And that process usually it's very fast. And also the volume will increase. And that I understand, which is a fat, later on becomes oil, then with the water. Okay, like a soap. Like a soup, sorry. So that's easily understanding. But how about the backwards? If we do this way, I melted the chicken soup, then we put it back into the refrigerator. So let's just say refrigerator. Let's say 4 to 5 degrees Celsius. Then a couple of hours later, it will become a semi-solid fat. However, this process is not completely reversible. Same as a water sorption and desorption. When the liquid becomes a solid or semi-solid, usually it's a release heat. It is a very slow process, and the volume is decreased. Now, in the chicken soup, we have a various fatty acids, including triglycerols. Now, all kinds of the fatty acids and triglycerols, they composed by various melting points. So for example, let's say stearic acids, the melting point is relatively high. That could be go to 60 to 70 degrees Celsius. And then oleic acids, the melting point is relatively low. Sometimes it's like 10 to 15 degrees Celsius. And then linoleic acids is even low. How low it is? -5 degrees Celsius. So you go the reverse process. The different fatty acids, the triglycerols in the chicken soup, they were not being uniformly all of a sudden become a semi-solid. So become a mixed fatty acid, triglycerols with different melting points. Therefore, what will we end up with? It will become a unsoluble crystallization status. With this insoluble crystallization status, it's end up with various polymorphism. Now, basically, there is three different types of the polymorphism. We call it alpha, beta prime, and beta. So our textbook, if you look at the Dr. Feynman's textbooks, they will talk about this. You have a gamma, this you have like a beta 1 and beta 2. It looks like it's very complicated, so we not talk about all these. Okay, we will be very clearly just do alpha, beta prime, beta. So how the research has been done? The research has been using X-ray diffraction. Very similar to the old time, we find the DNA double helix structure. And then they have three different layers, which is row 1, row 2, and row 3. So different layer. And then they find the basic morphology of these polymorphisms. So what's the alpha looks like? The alpha looks like somewhere like this, somehow like that, some like this, some like that, this, that, this like this. So what this means? This is an unorganized, unparalleled, zigzag pack. And we say it is relatively, we say it's a hexagonal stack. And from the low 1 and the low 2, between low 1, low 2, and low 3, there is a distance. So the space of rows 1, 2, 3 is relatively large. It's about 0.40 to 0.42 nanometer. The typical products looks like that is like egg mayonnaise. And we know this is not organized status. So, if the product is alpha polymorphism, we mentioned already, we need to be, it's dispersed, we need to be unified and stabilized. We will rely on an emulsifier. Then we talk about how we're going to determine the using of the emulsifier. We rely on the HLB value. Somehow it's between 0 to 20, and usually around 10 is the best one. So we mentioned about like twin, 20, 40 is the one we can use. So that's what we reviewed. So this is the alpha polymorphism form. The second one we'll talk about the beta prime, what it looks like. Beta prime is relatively very organized. We can see that. So the figure looks like this, then it looks like that, looks like this, looks like that. The center layer looks like this. Looks like this. And the last layer looks like that. So you can notice it's very interesting. The layer here, like this, like that. Now we draw like this, but ideally this angle should be 90 degrees. So how we say it? It's organized perpendicular stack. Perpendicular stack, and the space distance between rows 1, 2, 3 is a little shortened, so it is around 0.38 nanometer. And this organizer status is very important for the quality of the foods. This typically we will see is a manufactured margarine, shortenings, and also some cakes. Because why? This very organized beta prime form will give you a smooth texture plus a shiny surface. And also give you some of the cooling feeling of the mouth when you eat it. So that's why it looks like a cake. It's really nice for the, we talk about the sensory evaluation. Okay, so that's one. Now, how about the last one is beta? The beta is, they say it's more organized. So what does the beta looks like? It's easy. It's completely perpendicular from the row 1, row 2, and row 3. So it looks like this. The formation looks like that. So we can see it's well organized, parallel, or we say parallelogram stack, and very compact space, so only less than 0.36 nanometer. So this typically is, we had sunflower oil, some canola oil, or oil products looks like that. We talk about chocolate. We do want some type of the chocolate. It looks like that is very compact because it could avoid the blooming, which means avoid the fatty acids. That's with white color, fatty acids migrate to the surface. So this is very brief. We just talk about what the polymorphism looks like. So the idea will be looks like, because the fatty acids composed by liquid status, when they cooling down in the refrigerated temperature, they will not be completely reversible, not uniformly become a semi-solid. Some will become a semi-solid. Some is in transition steps. It depends on their melting points, depending amount of the saturated and unsaturated fatty acids. Then they could be composed with three major different polymorphisms, and each related to different type of the foods, and also related to the food quality. Okay, so that's a very briefly. We end up with this section talk about the polymorphism of the fatty acids, and I have a slide to talk about that. Now, regarding the fatty acid melting points, we already mentioned saturated higher than unsaturated, cis higher than less than trans, short chain less than long chain. We already talked about that at our introduction parts of the fatty acid section. Okay. So now we end up with the last section. We're going to talk about the antimicrobials, because this is the one we did in our lab for lots of the research, and also it's belonging to the fatty acid section, so we want to talk about this. So first of all, the antimicrobials, lots of the commercial antimicrobials that are short chain fatty acids. And we gave some of the examples. And we'll give more examples. Second, most of these are natural, existing, originally. And then later on, we can use chemical manufacturing. And if they apply on the food products, let's say applied on foods, especially like meat and fresh produce, they need to be certified. Or we say approved by USDA, FSIS. So that means the United States Department of Agriculture is indicate food safety and inspection service, recognized as GRAS status. What means GRAS? That means generally recognized as safe. So how they're using, they could be used on surface. That means you could use dip methods, could use spray. And they also could use as ingredients. So these are the methods what they're using. Now the last one, it's very important. Lots of these antimicrobials, if you look at, there is some restriction. What means a restriction? They have to use close to, or we say same as their pKa value. We're going to talk about this real quick. So give them some of the restrictions. This ends up with most of these antimicrobials achieve 1 to 2 log unit reduction. And lots of them, we say it's a static, which means inhibit the bacteria, not really like killing them, okay? So these are the overall. We talk about those commercial antimicrobials like short chain fatty acids. So we're going to give you some of the examples. Then we go back to talk about the mechanism behind it. The first one, CH3 acetic acid. CH3COH. That's acetic acid. Acetic acid, it's a commercial name. The pKa value is lower, around 4.2. Acid environments. Now where they come from? This comes from vinegar. What type of the microorganism it will be effective? And I tell you originally, this is more effective for fungi than bacteria. So originally people find it's very effective for the fungi. Later on find that they can curing certain foodborne pathogens of bacteria, like E. coli, Salmonella, Listeria. What's the concentration? And we find it's very low. Originally around 0.1 to 0.3%. So that's acetic acid is the first one. The second one, that's a one is it's a very old short chain fatty acids with a benzyl group is benzoic acids. Benzoic. Make sure. Benzoic acid. Benzoic acid, the pKa value is also very low, around 4.5 to 4.6. Now, where it comes from? That comes from cranberry. The food resource originally comes from cranberry. All other berries, major for cranberry. There is a certain research has been done with the cranberry. They find the cranberry juice could be improve the kidney function, which is a metabolic function, and they could somehow to help the body to against the urinary tract infection. So that's a cranberry. Now, what's a microorganism will be killed? Now, both for fungi and bacteria, but also originally found from fungi. You know what's the concentration? 0.3%. Okay, that's benzoic acids. Next one. Next one, people get familiar with that. CH3, COOH, COOH. So what's that? Acetic acid, lactic acid. That's lactic acid. What's the pK value? 4.2. A little bit higher, 4.8. Where that come from? Obviously fermented food. Dairy products for lactic acid. What's a bacteria can kill them? It's bacteria. Better than fungi. The good thing for the lactic acid is a wider range of the concentration, somehow between 0.1 to up to 2.0%. Sometimes they use 2.5%. But later on, people find if you're using 2.5% because it's a weak acid, but it's pretty strong, so they will cause a discoloration, which means a yellowish of the chicken muscle. So later on, they right now not always using lactic acid. They are combined with citric acid. So have a citric acid and a lactic acid blender to improve the quality side effects of the color of the chicken muscle. So that's lactic acid. The next one, I believe it's probionic acids. What looks like CH3, CH2, and COOH. So that's probionic acid. That pK value 4.3, coming from Swiss cheese. Better for fungi, then bacteria. What's the concentration? 0.3 to 0.5%. That's probionic acids. Last one, this one CH3, CH has double bonds, and then COOH. That's sorbic acids. Sorbic acid is a very old one. And their pK value somehow close to 5, but originally still 4.8. Okay, where it comes from? Berries. Different berries. Effective for fungi, for bacteria, around 0.8%. That's sorbic acid. So they're very interesting. Right here. It's like a pentadiene structure. Okay. Sorry, that's 0.123. Made a mistake. 0.120. So these are the very typical, the short chain fatty acids they use in the food products. At the beginning, when people are using. So we're gonna go back to talk about what's a pK value. So the pK value we listed here, it's very low, it's acid. So you have 4.2, 4.5, 4.8, 4.6, 4.8, not even above 5. So what's a pK value? We mentioned earlier, all these fatty acids, weak fatty acids, we write like this. So that's a weak fatty acids, a weak acid. This could be, have a reaction, reversible. Become RCOO, release the protein. So you get something, a different concentration. So what's a pK value? The key pK value is a pH value. Is the pH value at which the concentration of the undissociated status is equals dissociated status. This is called the pK value. Now, because the pK value of these short chain fatty acids as a earliest recognized commercial antimicrobials, there is this restriction. Now they're used in our food products. Let's say a meat product. What's the average pH of our chicken or beef? The meat pH, is around about 5.5. Could be low, 5.0, or could be higher, 5.7, no more than that, otherwise it's become DFD. So average about 5.5. And you compare to here, you can see the pH value is averagely around 1.0 pH value unit increase, which somehow represents the ideal pK value will be tenfold decrease. So that's why you are using these commercial antimicrobials on the meat products. You will see a limited limited antimicrobial impacts. It's about like 1 to 2 log. I don't see anything. Sometimes even less than 1. Average about 1 log. That means killing the bacteria is 90%. It's not that much. Now we want to dig a little bit more. Why they can kill bacteria, and why they are the impact is limited? The pK value is one of the reasons, but there's other reasons. So we can talk about the mechanism between them. So I have RCOOH, and we talk about will be released, become dissociated one, and with proton. So I have a bacterial cell. Is just draw it here. Okay. It's like this. Once they are going to attacking a bacterial cell, there is a restriction. What's the restriction? Is only undissociated one will go. So only RCOOH formation will be go inside. The dissociated one will not go inside. And then inside of the bacterial cell, the pH usually around 6 to 7. A normal bacterial cell grow in the lab about the neutral pH. And then at this neutral pH, what happens? The reaction goes this way. Because in the acid environments, the more proton concentration, they go that way. So in the bacterial cell inside of the body, they go the right way. Therefore, inside of the bacterial cell, they dissociate to become dissociated format, and the proton comes out. Now, the proton comes out. This is acid. That's really bad. We don't want that. So how we do? The bacteria need to repel this out. Now how they repel this out? They need to expense within the spending something. What they are spending? We in food microbiology, food chemistry. Okay, we need to do something little difference. We don't want to like. We want to do this little complicated. So what's this? Everybody should be very familiar with what it is. You go here, you go here, you go here. So that's ATP. So inside of the cell, bacteria has to hydrolyze ATP, become ADP, and the phosphate. This rely on help of the ATPase to accompany with repels proton out of the cell membrane system, cell wall system. And this is the energy. So which means they're going to expend the energy. That means finally they will be exhausted, okay, or energized. So that's a very simple mechanism to killing the bacteria. However, in the environment, bacteria has to be accustomed to. So what happened? They have their compact way to do. They usually exchange with potassium. Let the potassium go inside and exchange with with the protons. And sometimes they will be activate some like HPR, heat stable proteins, those kind of factors to create acid resistant bacteria. Now, once acid resistant bacteria created, it's very bad. Because if you are on the beef carcasses, you are sprayed with all of these commercial antimicrobials, and they are becoming repeatedly using. You are not killing all the bacteria. Some of them become acid resistant bacteria. If you further do cooking, they need a longer time to cook because they will create cross protection. For further cooking or antimicrobial treatments. So that will give you the issue of these antimicrobial resistant bacteria. Okay, so this worried with industry a lot of the years because of this restriction of the pK value and also the limited antimicrobial mechanism. So they worked with food chemists. They find a way they could relatively improve the pK values range. So how they do? Now how they increase the pK value range of the application. So we can using a benzoic acids as an example. What they do. So we had a benzoic acids like this. That's a benzoic acids, everybody knows. And I'm going to start working with ethanol. I'm not starting working with ethanol. I start to work with a methanol. Now how they work them? That's very easy. These work together, release the water. So what it looks like? Released with water, create a very interesting products, which is CHC. What's that? Benzoate. That's called a mesobenzoate. I need to make sure my spelling is correct. Yeah, mesobenzoate. This is called mesobenzoate. Now, what's azo? Ate means? That means ester bond. Ester bonds. Or esters is created, so like that. Okay, now it works. So people are going to do more. How they do? Again, still we had a benzoic acids. Let's go ahead and work with the ethanol. Okay, so we work with the ethanol. So what it looks like? We release the water. That's not a problem. Then this one will belong. So right here, remember, lose the water. Okay, so become that's called the ethanol. benzoate. Okay, now people say, you could do this more. Okay, what they do? They do more and more. Okay, they go here. They have propanol. So we do this. So I skip some. Go here. Release water. And they have a propanol. Propel benzoate. Okay, they can do on and on and on. Now what happened? This helps, number one, increase pK value from 4.2 to 4.8, could also way go to 5.5 to even 8.0. This means you can use at a neutral status even to not only increase the range of the pH products, it also will be decrease the side effects, like will be decrease the corrosive. So that's really good. Increase the pK value. However, there is a side impacts. So you can see here, this CH2 is become more and more. So more CH2 chain added, which means more alkyl added. What happened? Less water dissolved. So people notice this problem. It's more and more pK value, but it's less water dissolved. We don't want it, because we want them water dissolved. Like I said, if it's ethanol dissolved or chloroform dissolved, especially we work in the lab to do the validation study, we don't even know what's the function of comes from. It's could come from the ethanol or chloroform, which means even we do a lab test, we need to have a control groups for the ethanol itself to see is that the antimicrobials coming from the benzoic acid itself, or methyl benzoate, or it's coming from alcohol. So this bothers people. Therefore, what happened? This method is stopped somehow middle 1970s or 1980s. Then people come out with something. That's interesting. I have acetic acids. So that's why the chemistry is important. Okay, you have this guy here. What can be reacted? A salt. The using sodium chloride. Okay, not sodium chloride, sodium hydroxide. When this comes, what they do? This becomes and the water. This comes out. That's really nice. Can be dissolved in the water. So sodium acidic. Sodium acetate, what people say. Okay, now this comes with this guy. We don't think it's enough. So what we do? We react it with another acid. Acetic acids. And this comes with what? That's a very interesting stuff. CH3, O, H, then here, What is this guy? Sodium diacetate, 2.5%. You can go ahead to buy hot dogs or daily meats. I guarantee you, you look at the label, the antimicrobial ingredients, in addition to nitrite, unless it is organic process, it will using is sodium diacetate, is this guy. Because these chain you added, pK value increased at around 5.5 to 6.5, then you add sodium, it's dissolved in the water. That's why you see sodium diacetate, 2.5%, is widely existing in all of those ready-to-eat meats. And the story is that they started to think about this way, find it less dissolved in the water, and they do that guy. So that's why you look at all these labels. Sodium diacetate is most used antimicrobials, recognized as GRAS, or those ready-to-eat meats. Sometimes they work with potassium lactate, PL, potassium lactate, about 0.5%. That's another story. But at the beginning when they do, this could low down, this could increase the pK value. Also with sodium, it could be dissolved in the water. Okay. I have a little bit of space. We're going to talk something in our lab of what we did. Okay. We did is so-called a Sanidate 5.0. So what is that? That is acetic acids working with hydrogen peroxide and then become a very interesting stuff is this guy. This is called a PAA, peroxy acetic acid.